Okay, so I hope you are able to hear and you are able to see my screen now, right? So this is about me, my brief introduction, and in this week we are going to see that uh, first we will try to see the concepts behind to solve the assignment two problems, and after that we will clear all the queries and we can discuss those topics. Okay, so I hope that should be fine. So let us move ahead with uh, question, or I would say rather, let's take a look on the basic expressions which are gonna use in today's week assignment problem solving. Okay, so now in last week we have all studied about electric loading and magnetic loading, right? So now when it comes to transformer, okay, in transformer design, those electric loading and magnetic loading, they are very important. Okay, so like I discussed about that, what are the electric loadings? Electric loading is equal to number of turns into current in that winding, right? This unit of it is ampere turns. Okay, now in a transformer we have something called as a window, right? So window is nothing but, so here the winding will be placed. Okay, so this area is width of window and this length is height of window. Okay, so
Okay.
now I hope you are able to hear me, Rajni, right?
Yes, sir, I can hear you. Actually, it's a problem is at my end only. Sorry for that. Now I can
Okay,
hear you well.
okay, no problem. So now the window factor we wanted to find out, right?
Yes.
So this is called as window factor, which is nothing but copper area in the window, copper area in the window divided by total window area. Okay, so what will be the total window area?
W into W
Yeah, HW into WW, like height into width, because it will be a rectangle, right? So
rectangle. Yes.
uh, let me write it in units. So if we divide by AW, so Rajni, when or Dinesh, I think your mic is on. So when you are not speaking, kindly turn off your mic so that noise could be minimized for the recording. Dinesh, a lot of noise is coming from your side. I'll have to mute you. Okay. Uh, okay. Fine. So window area is nothing but height of window into width of window. Okay. This is sorted. Now copper area will be some portion of it, and that would be taken by we can calculate from the placement of that winding, right? So if generally we are given with the this window space factor, this kW is nothing but window space factor, right? So let me write it here.
So KW means window space factor or winding factor? I used to see winding factor somewhere like
No,
KW
no,
means.
winding factor is entirely different thing.
Okay, okay.
Winding factor is, how much of let's say, let's suppose winding is producing some mmf, so how much is the fundamental, like winding will also produce some harmonics along with the fundamental mmf or flux, so that is known as winding factor, that we can discuss in some
Later.
other day, right?
Okay,
But that is entirely different from this factor, window space factor.
okay, sir.
Okay.
Okay, yes, sir. Yes.
Yeah. uh, I just wanted to turn on my camera. I just give me a second. Okay, I think eventually it will happen. Okay, so this is about window space factor, right? And this parameter you might be seeing quite frequently while solving the problems from assignment 2, I guess. Right? And this is the space, this is the factor by which our window space available in the core, inside the core, that has been utilized. Okay. So this is very important parameter. So we will keep that in mind. Okay. And is there any doubt regarding that?
I have a question.
Yeah.
KW means you written like a copper area in the window divided by total area, total window area. What about
Right.
copper area in the window? What exactly it means, sir?
Yeah. So let's suppose we have a winding. Let's suppose we have certain number of turns in the winding, right? So
Yes.
we keep winding, and it goes until some portion of this window inside. Similarly, on the secondary side, right?
Yeah, yeah. The second design.
If you wind just one turn, then it will be just around, wrapped around the core. But if you keep wrapping around the core, this area will keep getting increased.
Mm-hmm.
So are you getting the idea? It can reach up to certain extent only.
Okay.
That factor is called as this copper area divided by total window area, because it cannot be one, then there will be insulation problem. If both the wires will be connected with each other, then the possibility of short circuit fault will be there,
Mm.
right? So
Yes.
to
Okay.
to maintain the electrically insulation between two windings or multiple windings, we give some factor there.
Okay,
Okay, I
sir.
hope. Yeah.
Yes, yes, yes.
Now, what about copper area in the window, or what about the copper area? We have talked about window area, we have talked about window space factor. Now talk about copper area. So what will be the total copper area in the transformer or winding? Can we calculate in terms of any standards?
Copper layer. KC for mm square?
Sorry, which one?
KC for mm square, like a copper in the grams somewhere. Weight we will take, no?
Uh, mm, no, like how much? See, so what is copper area basically? So how much the wire is wrapped there,
Wrapped on
and
the folds, like what matter
yeah,
means.
so wrapped on the core, right?
Core, yes.
Yes, including primary winding and secondary winding if we have two windings. Okay,
Mm.
so we generally represent in terms of number of
N1,
turns,
N2.
n into I,
Uh,
right? This
mm,
is the known terminology, right? This is
mm.
mmf, nothing but the mmf. Now this is nothing but total number of turns in primary conductor, sorry, on primary side, into area, here we need area, right? So what I mean to say here, that if we know the area of single conductor, okay,
Hmm.
then if we multiply by number of turns there, that will be our total copper area. No.
So
So
pi d square by 4
number of turns into area of single
turn
turn or conductor.
conductor.
Okay. So we can calculate area of any single conductor, right? And
Hmm.
simultaneously, if we know the number of turns, then we have total copper area of any given winding. So let's suppose we have primary and secondary winding. So we will have N1 into area of conductor 1
One.
plus N2 into area of conductor 2. Okay. Now I
Yes.
want to convert them in some known terms, in terms of MMF. Can we do that?
Mhm. I by a current density. No, I'm not getting properly, sir. So number of turns into area of single conductor you given. You want to ask which one? Like
Can we relate
MMF,
it
you
with
have to convert into
MMF?
MMF.
Yes, yes. Had to relate it with MMF to be precise. So, do you know any relation between current and area of conductor? Some parameter, what is
Current
called
density, sir.
current density? Exactly. That's what I was looking for. So, that is current density. So, current density is nothing but,
Current for unit area.
yeah. So, current in the conductor divided by area of that conductor. Okay.
Okay, sir.
So, that will be current density here. Now, if so, we know that area of that conductor, it is A1 here, right?
Mm.
And we know current density here, and we will manipulate this equation into n1 into I1 by current density of the primary conductor. Similarly, n2 into I2 divided by current density of the secondary conductor, right? And so now, if I assume that n1 is equal to n2, like both the sides have similar number of turns and both the sides have the same current and both the sides have same current density as well, then you have total copper area is equal to how much?
2 into
N, sorry, yeah, you are right. 2 into N into I divided by Z.
J.
Yeah. So this is your total copper area. So now you know everything about your window space factor in the transformer, right? So if you are asked about any terminology, I hope you will be able to deal with that.
Okay.
Any doubt here?
Sir, I have a question. Like N1 equal to N2, like it's a step down or step up transform easy to do, no? So why N1 equal to N2?
No, no, it's just a special case, right?
Okay.
Yeah. When you are making any step up or step down, then these values will be different. Just
Different.
for the
Yeah.
simplify this.
Okay, sir. Then
Yeah.
clear, sir.
Go ahead. Any other doubt?
At mine, no, sir. It's very clear
Okay.
for me.
Okay. Okay. Thanks. Anybody else? Okay, if not, then we can move ahead. So now our next objective is to calculate the KVA rating of the machine, right? This is another most important parameter to solve the problems. Yeah. So what will be the KVA rating? Voltage into current, right? Voltage rating into current rate. Now, voltage will be nothing but induced EMF. What is the expression of induced EMF? Do you know in the transformer?
E equal 4.44 into pi into
Mhm.
Z
Z
N.
N.
Pi Z
Okay.
N. This much moments.
Oh, okay. So this should be the amplitude of the EMF, right? Which means the maximum amplitude of the EMF, right? And here this phi should be phi, because
Pi.
if you are providing sinusoidal supply, then you will have sinusoidal flux approximately, and then you will get to have sinusoidal distribution of flux density in the machine, right? So for that, we are dealing in terms of amplitude. Okay. So what is Z here?
Z is the number of conductors.
Number of conductors. But generally in the book, it is written number of turns, right?
Number of turns.
So what is the difference between them?
Oh, I think NEC is not there, sir. NEC is for rotational missions. So there it is N equal to RPM will come, no?
Yeah, yeah,
Here there is no N actually.
yeah. So
Or
here actually
either N or Z. It means number of turns. It
yeah,
indicates, yes.
yeah, number of turns. So there are
Number.
different difference between them, but that will come in the machine distribution when we have two different wires, two different conductors to contribute to a single turn, that is known as double layer or single layer winding. But here it will be frequency into number of turns. Am I right?
Yes, sir. Yes.
Yeah, yeah. So that is your voltage rating, right? And current we have here. Current, generally in terms of current density, if we can write, that would make our life easier. So E into Z into area of conductor. Okay. So since you are, designing and you are going from bottom to top, so you must be, at the condition to decide how much area do you have so that you can supply that much current there. So that's the logic behind it. So yeah. Now can we relate it with window factor? This term, entire term, KVA rating, in terms, it is, we have come up to E into J into A, right?
Hmm.
Sir, this is RMS or maximum value?
This is maximum value. This is maximum value. This is amplitude. So our KVA rating. Rating is what? The maximum value your machine can hit.
Yep.
So earlier we have derived that 2Ni by Z, right?
Total copper area 2Ni by G.
Yeah. So it is nothing but what? Window space factor into core area, right? Here you can see, or window area. So copper area divided by window area is nothing but window space factor, right?
Yes, sir.
Yeah. So we can use this expression here, Kw into Aw into J divided by 2 is equal to Ni. So Ni we can use as Kw into Aw into J divided by 2. Okay.
Okay. Okay, sir.
So here at the
Yeah, yeah.
place of I, it is nothing but basically voltage into current, and here I is equal to Kwaj divided by 2n. Okay. E into Kwaj divided by 2n. Okay, this expression you might have seen in during the lectures as well, right? So this is very important expression. And if you consider here EMF, it is total EMF induced in total number of turns. If you have EMF per turns, like replace E with ET, ET is nothing but voltage per turns. Then KVA is nothing but ET into KWAW Z divided by 2. Okay. Any doubt in this?
Sir, E equal to E play what it is exactly? The voltage per turn you written over here. What exactly it is?
Here, you are asking here only?
There and little bit up also. E equal E.
This one.
No, no, next.
This one?
No, down only, sir.
This one?
No, next up.
Acha, here.
Yeah, there.
So I
E.
have replaced with total induced EMF by induced EMF per turns. By
Okay.
single turn, how much EMF is getting induced there? Did you get that?
Okay, sir. Yeah. Now got it. Yes.
Yeah.
So there is a turn.
Okay. Any
What
other
about
doubt?
N,
Yeah.
sir? What about N?
N.
Two.
What about N? Yeah. So here, see.
One
So
turn,
this is.
that's why you written ET.
Mhm.
A kVA equal to actually formula what we got is kVA equal to E into kW into AW into J by 2N.
2N. Yeah.
Okay. And coming to here, E equal to E turn, we written voltage by turn.
Yeah. So see, this is the voltage and
And
this is
turn
the
N.
total number of turns.
Yes, got it, sir. Now it's okay. E by N indicates the ET. Okay.
Yeah, exactly.
Yes.
Yes.
Okay, sir. Yeah, please.
Okay. So now if we can plug in the value of ET also, that is nothing but 4.44 into F into phi m. Here we will not use N because N has already been utilized in ET, right? Into KW into AW into current density divided by 2. Okay.
Okay.
Now, if we can further simplify it, it will be 2.22 into F into phi m into KW AW into J. So this is your KVA rating of the machine. So it will be used very widely while solving the problems. Okay.
Okay, sir.
Fine. So let us solve some problems first, right? Since we have
Okay.
derived this much. Have so we will see the first here the first problem that we need to calculate area of net iron of a single phase 50 hertz core type transformer with voltage per turn is given 10 volt and current density is given 2.8 amps per mm square and maximum flux density is also given, right? So can we calculate the area of iron only? So how will we proceed for this problem?
Next, the area of net iron. So we have to find out AW, na, sir? Here?
No, we have to find area of iron,
Area of net iron. Okay, this area of iron.
area of core basically.
Area of core.
Sir, we can calculate 5 max.
Yeah, exactly. We can
We
calculate
can
5
calculate
max.
5 max from the E
Yeah,
formula,
yeah, right.
and then we can equal that to B by A. I
Exactly,
equal to B by A.
exactly. So there you will get the area of iron. So I hope you have seen the problem. Anyway, I'll write all the parameters. So this voltage per turn is given as 10 volt, which we will equate it with 4.44 F5M into number of, no, okay. Now frequency is given as 50 hertz, right? So we can calculate 5M, which will be 10 divided by 4.44 into 50, which will be equal to, let me calculate it, 10 divided by 50 into 4.44, which is nothing but 0.045 Weber. Okay.
Okay, sir. Webers.
Now we are given with the flux density, maximum flux density, Bm, which is 1 Tesla, right? So Bm will be equal to nothing but 5m divided by area of iron,
5 by 8.
which is what we need to calculate. So area of iron will be equal to 5m divided by Bm, which is nothing but 0.045 divided by Bm is 1 Tesla. So you get 0.045 meters square. So that much is the area of core.
Core.
Okay. Got it?
Yes.
Any doubt in this part? Now,
Sir,
the next, yeah, go ahead, please.
it's clear, sir. There is no any doubt. It's
Okay.
clear.
Let's move on to the next part. Okay. So see the second problem particularly. Okay. For the 100 kVA, 2000 divided by 400 volt, these are the turns ratio basically, and 50 for single phase core type transformer. Assume voltage per turn is equal to 10 volt. Flux density in core is given 1.1 Weber per meter square. Current density is 2 ampere per mm square, and window space factor is equal to 0.3. So here again, window space factor is coming. So you have to, correlate with window space factor, whatever is required here. Now you need to calculate primary winding conductor area and secondary winding conductor area. Okay. See the problem carefully and try to give it a minute.
So they given kVA rating of the transformer, no sir, and they given in one voltage also they given a V1 and V2. So we can
Right.
get current over there, no?
Yeah, you can get current, and
Current
that should be the
primary current
objective
and
there. Yeah.
secondary current we get it.
Yeah. If you get current, right, then you can get area if you know the current density there.
Yes, sir. I
Yeah.
know the
So
current density. They given current density as a 2 ampere per mm square.
right. So you are given with current density. If you can somehow calculate the current, you will be able to calculate your conductor area. Got it?
Yes, sir.
Yeah. So let me also solve there. So you are given with, voltage per turn is equal to 10 volt, right?
Voltage per turn equal to 10.
Yeah.
ET 10.
10 volt. Now you can calculate primary number of turns. Okay. Can you calculate primary number of turns? Because primary voltage is given, or rather voltages are given 2000 divided by 400 volt. Okay. If you are given with the voltages, you can calculate because voltage per turn you are given. So 2000 is the
By
primary voltage divided by voltage per turn. So it will lead to number of turns in primary winding. So you have total 200 turns in the primary winding. Similarly, secondary winding will have how many number of turns? So total voltage on the secondary side, 400 divided by 10.
10.
So
40.
it will be 40.
40.
Right. So you are done with the total number of turns there, right?
Yes.
Now, can you calculate the current? Because you are given the kVA rating of the machine, right?
Yes.
So kVA rating. So now our objective should be to calculate primary current. That should be equal to kVA. That is nothing but 100 kVA. Right? 100 kVA it is. So 100 kVA divided by
2000.
divided by 200.
Oh,
Isn't it?
sorry. 200.
Oh no, sorry. You are correct. 2000 only.
2000 na
2000. Yeah.
power
NP
by
is 200. But here to calculate current, we should have kVA divided by VP. Okay. So VP is nothing but 2000.
2000.
Okay.
Okay.
Now can we calculate it to 50 amps, I guess. 50 ampere is the primary current.
Yes, 50 amperes.
Similarly, secondary current should be how much? Voltage in the secondary winding is 400 volt given, right?
400.
400. So here now it should be 1 by
250.
4, 250 amps. Exactly.
250.
So you are done with the current. Now you know the current density. So I think you can calculate the conductor area in HV as well as in LV. So what
Yes.
will be the HV conductor area? So what is the value of current in high voltage conductor or HV winding, high voltage winding? So high voltage winding is which one, primary or secondary?
Secondary.
High voltage winding is
High voltage one
primary
is
winding.
primary.
Primary.
2000. It's
Yeah.
step.
Yeah. So there in primary winding or in high voltage side, our current is 50 amps and current density is 2. So conductor area is 25 mm square, isn't it? Because current density is generally given in ampere per mm square. So
square.
do not get confused here, right?
Mm.
So that is a very standard unit of current density. Similarly, LV conductor area is current on LV side is 250 amps
250 amperes.
divided by 2 mm square. So it will be 125 mm square. So on high voltage side, conductor area is smaller compared to the low voltage side. Why? Because we have to use thicker conductor to accommodate the higher current. Right? On the
Mm.
LV winding side, since their voltage is low, but then current should be
High.
high there to maintain the power balance from the primary to secondary, right?
Yes, sir.
So for that purpose only, we have higher conductor area on the secondary side to cater the higher
Current.
amplitude of the current.
Current.
Yeah. Any doubt in this part? Okay. If not, then let us move ahead with the third question here, right? So I hope you can see the third question. Kindly read it and try to think something there. So basically it is said that we have a single phase 250 volt 50 hertz transformer built from a stampings having a relative permeability of 1000. So did we talk about relative permeability in the last lecture?
Mu R values, sir.
Mu R value, exactly.
Mu R values. Mu naught and mu R, they are absolute permeability 4 pi into 10 power minus 7. And it's a depend on material. No? So mu R equal to here 1000.
Yeah, so for air, we discussed mu R is equal to 1, and as
One.
high the permeability of the machine, the better core is there for our operation. Right?
Yes. It allows
So,
the flux lines more, no? Like permeability.
yes, it can cater more flux. So the length of the flux path is given as 2 meter. The area of cross section of the core is given 1.5 into 10 raised to power minus 3 meters square. And primary winding has number of turns is equal to 750. Now a new terminology which is a stacking factor, which is given as 0.88. Now we have to calculate maximum flux density there. Okay, so what is the stacking factor first of all?
Insulation. It's a telling insulation. No, so stacking factor will define like.
Yeah. So in our machine, there will be current flowing, right? And there will be flux flowing. So let me just explain. I drew the core there. Yeah. So let us suppose by this winding, with this winding fashion, you will have a flux flowing in this fashion, right?
Yes.
Now, if you have flux flowing, then you will have a circulating current. You keep your thumb in the direction of flux and you rotate your finger. then the direction of curl of your fingers will give you a direction of circulating current, which is known as which current?
Eddy current.
AD current, exactly.
Eddy.
AD current. And that is why you have AD current losses in a transformer core or in any core where flux is flowing there, right?
Yes.
And to avoid that AD current losses, which can be significant, we keep multiple laminations sandwiched between, we have insulations, right? So that AD current should be avoided. So we have multiple laminations. If you are building for 10 mm of lamination, so you could have approximately 20-30 laminations there. So your core should not be solid, right? So it should not be solid core. It should have certain number of laminations to avoid this phenomena of AD. So that is why we use a stacked rings. And with the help of these stacks, what we are doing, that our gross length or gross area of core is less compared to the total length, right? Because you have insulations also in between. So that is what a stacking factor. A stacking factor is nothing but your total length of core laminations divided by total length of lamination.
Okay.
Total length of core. Okay, so it will be always less than 1. Typically, it varies from 0.9 to 0.95. So that value is given here with us, 0.88. Okay.
Okay.
Now we need to estimate the maximum flux density in the core. So I hope now you can calculate.
Yes, sir.
I hope you have seen the problem carefully. I'll again write all the parameters there. Yeah, this third problem. Just try to solve. I'll come in a minute. Do you have any answers here? Okay, so let us go ahead with the solution. So we have 250 volt, 50 hertz transformer with mu r is equal to 1000. Okay, the length of flux is equal to is also been given. So area of iron is given as, sorry, area of cross section is given. So (1.5 into 10 to the power minus 3 meters square), and N1 primary winding number of turns is equal to 750. A stacking factor is equal to 0.88. We need to find the maximum flux density. Okay, that's all. Now the net iron area will be, okay, how much? We are given the cross sectional area of iron. The net area of iron will be multiplication of a stacking factor into the cross sectional area, which is nothing but 0.88 into 1.5 into 10 to the power minus 3 meters square. Since we need to calculate Bm, we are given with voltage, so we can relate with the famous expression of 4.44 FIN, right? So the voltage is nothing but 250 is equal to 4.44 into frequency we are given with 50 hertz into phi m we are not given. So we can write Bm into area of iron into number of turns in primary winding is equal to 750. And this AI is also we have calculated here. This is the value of AI, right? So which is nothing but, let me calculate 1.5 into 0.88, which is 1.32. So can we calculate Bm now?
Yes, sir.
Bm is equal to 250 divided by 4.44 into 50 into 1.32 into 10 to the power minus 3 into 6. Let me calculate it. Into 1.32 into 50, nothing but 1.1375 Tesla. So this is the maximum
Correct.
value of flux density in the core. I hope you are also getting the same. Okay,
Yes,
any
sir.
doubt in this part? Okay, if not, then we can move ahead with the next problem. Yeah, so see carefully the fourth problem. Okay, a single phase 250 volt. Yeah, just a second. Read the problem, please. We have a single phase 250 volt 50 hertz transformer with relative permeability of 1000. The primary winding has 750 turns, the same scenario. Core area is also same, stacking factor is also same. Now the magnetizing MMF is given 2000 ampere turns. Okay, so it is just an extension of the last problem. And you are given with the magnetizing MMF. Now you need to calculate the flux in the core. as well as the magnetizing current. So I hope you remember in the last lecture we have discussed about active component and magnetizing component. Magnetizing
Yes, sir.
component is used to magnetize the core, right?
Core and active component for losses.
Losses and load.
Load. Yes.
Okay. Can we try to solve this problem here?
Yeah.
Can we calculate flux in the core as well as magnetizing current? So what could be our approach? We will discuss about approach. So flux in the core we can directly calculate from our EMF expression, right? Or we have already calculated that, right? If I am not wrong. Flux density we have calculated, and we are given with the area of our iron, right? Net area we calculated. So I think we can calculate flux from there. So see, here we calculated flux density. We have the net iron area. Can we calculate flux in the path? Maximum flux in the core? And nothing but Vm into area of iron.
Area of the cross. Yes.
1.1375 into iron area is nothing but 1.32 into 10 raised to power minus 3. Okay. So if you multiply this expression, you will get
1.50.
1.50
15 10 power minus 3.
10 raised to power minus 3 Weber. So I hope regarding the first part there is no confusion. Now we need to calculate magnetizing current. So we are given with the magnetizing MMF, isn't it? We are given with magnetizing MMF. Now the magnetizing MMF is given and magnetizing current it has been asked. So we can directly relate it with number of turns. Okay.
Okay.
So magnetizing MMF component is 2000, which will be nothing but number of turns into magnetizing current.
Yes.
Yeah. So magnetizing current we can calculate. That is nothing but 2000 divided by number of turns is 750. Okay. Now, which value of this is magnetizing current? Like, is it RMS or maximum value? What is this?
Maximum value?
This is maximum value. So see, the MMF is given based on the maximum value, right? So it is already maximum value. So if you want to calculate RMS, you have to divide it with root 2. So this was the maximum value. Now we are dividing it with root 2 and you will get the actual RMS value. Yeah.
Maximum value 2.66.
Yeah, maximum value 2.66 and
And the
RMS
RMS value is 1.8856. 1.8856. Yes.
Right. Thanks for calculating. So let's see. I hope there is no any doubt in this part, right?
Yes, sir. No.
Yes, sir.
Yeah, go ahead, please, Dinesh.
Yeah, how we deduce that it is a maximum value of the current?
Yes, that's a good question. So see, anywhere if you are given with MMF, which is nothing but ampere turns, right? And there itself is included maximum amplitude of the current. So this 2000 is ampere turns. Here ampere unit you can see, right? And this ampere is nothing but the maximum current rating, because MMF is nothing but the rating of the winding. So rating is generally dealt in terms of maximum value. Did that answer your question, Dinesh?
Like in the problem, it is not written key. It is a maximum MMF.
Yeah, that's why I clarified this part. That's why, because in the problem it is not written. That's why I clarified this is the maximum value. So whenever magnetizing MMF is provided, because see, uh, MMF can be produced with DC supply as well, right? And AC supply as well. So with DC supply, RMS, average, all are same. But with AC, here we are considering how much see, whenever we discuss about flux, what do we discuss? Average, RMS, or maximum? Dinesh?
Maximum.
Maximum. So flux is being produced by MMF, right? That's why here we have to, because see, MMF is nothing but NI. Okay. Another equation is flux into reluctance, right? If you are dealing in terms of maximum flux here, because everywhere we considered maximum flux, right? So what will be your MMF? Won't it be maximum? And for it has to be maximum, I has to be maximum because number of turns is same. Did you get it, Dinesh?
Yeah, correct.
Yeah. Okay. So let's see another topic of circumscribing core, which is very important for solving next 4 to 5 problems. Okay. So what do you mean by circumscribing cores? Basically, it is there to optimize the design of transformers so that our wastage in the core should be as minimum as possible, so that we draw a circle around the core to calculate the optimum area of core. So let me talk in this manner. So yeah, we have a core here, right? Then you draw a circle. Okay, let me take the help of ready-made drawing. Okay, so you have a core there and you draw a circle around that core, right? And whatever the diameter of that circle, okay, there will be a relation between the width of the core and the diameter of the circle. So the to optimize it, the basic understanding is you reduce the diameter of circle as much as possible to optimize your core design of the transformer, right? So how can you reduce the diameter of your circle? Do you have any idea, or have you gone through the lecture of professor?
No, sir. Sorry.
Okay, no problem. So here you go ahead with multiple stepped core. Like, do not have a rectangular. You can have multiple stacked core. So here you have some portion like this and have some portion like this. Now, whatever the circle area would have been required. Now that is optimized in this fashion. I'm bad at drawing, but you understand that compared to this entire, entire area of rectangle, now you have reduction in the area of the circle here. So that is what is called as core stacking, or rather a stepped core. You step it in multiple steps, right? So the higher the number of stepped cores, the more optimized will be your design. But what is the price to pay for that? That assembly effort and price also will go higher for that manufacturing process. So now let us calculate. So this is the D. So D is nothing but the diagonal of the circle. Okay. And we are given with, so first let us calculate this for rectangular. Okay. What we can do, that gross area of your core, is nothing but how much? If the side of rectangle is given by A, then how much is the gross area?
A into A square.
A square. Okay. Now the diagonal D, can you relate it with the A?
Yeah, D equal to root of A square plus A square. A square is equal to A square.
Exactly.
A root 2.
A root 2. Okay. So this is the gross core area. Now the core stacking factor for, if you are considering here for a stepped, or no, we have to stick with this rectangular only. The area of circle, area of core, which is known as area of circle, which is nothing but pi r
Pi r
square, nothing but pi d square by
4.
Okay. So now you have this relationship between both of them, and the next step is net core area is equal to area stacking factor into this pi d square by, okay, this much we have to keep in mind. But once we go ahead or shift here on the stepped cross sectional, right, then we have to calculate this area. Another important thing is the ratio between both of them, right? So the ratio between net core area and gross core area, can we calculate it here? So see, you might be confused, like why I am trying to calculate both the areas. So a stacking factor, if you define in terms of area, that is also net core area divided by gross core area. Okay. Now for rectangular core, we have gross area is nothing but A square. Okay. And this net area is nothing but pi d square divided by 4. And D we can relate with is equal to A root 2. So pi into A root 2 square divided by 4A square. So how much will it come? 2A square. So pi by 2. Is it pi by 2?
Yes, sir, pi by 2.
Hmm.
It's a 1.57.
1.57. It will not be correct then.
3.14 Anna. 1 second. Pi divided by 2.
Because why I'm saying, because stacking factor
Here
should
it's
not exceed
1.5.
1.
Pi by 2 because pi is 3.14. 2 ones are 2.
Hmm.
1.57 is coming. Sir, it's 1.57 only coming, sir. Pi by 2 equal to.
Have we interchanged the term net and gross?
2 5s are 10 to 9. 1.57 correct.
Okay. Yeah. Have I think no, but this is correct. Okay. Let us solve in terms of D. P stacking is equal to gross sectional area is D square. Gross core area is circle. Yeah. So gross. We have interchanged the terms here apparently. So gross is nothing but the rectangular, and net is nothing but the circular. So rectangular is A square. We did the same thing, isn't it?
Yes, sir. Glass with same rectangle. That is square.
Okay. D square by 2. A nothing but D by root 2. So D square by 2 here. And pi D square by 4. Again, it should come as the same, right?
Same. D square cancel. 2 2s are 5 by 2. 5 by 2, 1.57.
Hmm. Cross section divided by gross cross section should be of course. I think it is interchanged in the lecture slide. So see, basically circle is outside, so area of circle should be higher than the rectangle because circle is
Yes.
circumscribing the rectangle. So in terms of gross, I think we should have used this circular
Yes.
area. Yeah. So now we have to just take a denominator instead of numerator.
Yes.
So 2 by pi it should be. So it is 63%. So 0.63.
2 by
K stacking should not be higher than 1. So it is 63%.
0.666. Correct.
Yeah. Yeah, so circle is circumscribing the rectangle. That's why in the gross core area we have to consider circle, and in the net core area, which is nothing but the rectangle.
Square.
So the idea is to minimize the area of circle as much as possible, right? So now in two-step core, let us see how much is the stacking factor here. Okay. So now this width is A, okay, and this width is also A. This width is B, and this width is B. Okay, I hope the drawing is better now.
Yes, sir.
A, A, this entire is B, this entire. So B, can we call it is equal to diameter of the circle, right? So B, we should replace it with D, D, since it is diameter of the circle. Now, net core area is how much? I think A into D for this block, right? Oh, no, 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 this is not here. This is up to here only. Look at, yeah. So this horizontal rectangular has the area of A into D, right? But D minus A. So A into D minus A. Are you getting how am I calculating this area of horizontal section? A into D minus A. Because see, this portion is not available in this core, right? This core is used here. This one core is used here only. Another core is used here, and another section is used here. So we are dealing about 3 sections. But since these 2 sections have equal area, so I am calculating for them that is equal to nothing but A into D minus A, right? This now vertical area is how much? Can we say A into D? Can we write 2AD minus A square is the net core area, right? And the gross core area is equal to, again same, pi d square by 4. And can we calculate any relation between D and A?
D and A.
Can we calculate any relation between D and A?
Yes, sir.
So there will be one angle. There has to be an angle, right?
Arc angle.
So see, uh, if you draw a line, a straight line here, rather, let me take the help of this line. Now can you calculate? There will be a theta.
Theta by 2 pi r. That one.
No. Here you have to use trigonometric identities. So cos theta
Is equal to root of a square plus
cos theta is equal to, let me see where I am saying
d
here,
by
b by h. So a by d, isn't it? Cos theta is nothing but base by height, right?
base by height.
So base
Yes,
is
sir.
nothing but a and height is d.
Yes, sir.
So wherever you are using a, you can interchange with a is equal to d cos theta. Okay. So this, if you will go through the lecture, you will find it. But even though I am explaining here that these are the manipulations have been done for calculation of a stacking factor. Now you just plug in there in a stacking factor is net core area is nothing but 2AD minus A square divided by gross core area is nothing but pi d square by 4. Is there any doubt in this trigonometry is A is equal to d cos theta or till or at any point?
No, sir.
Okay. So now A is equal to d cos theta. So now A will be d 2 d square cos theta minus A is equal to d cos theta. So d square cos square theta divided by pi d square by 4. Okay. Now d square and d square will get cancelled out. So 2 cos theta minus cos square theta divided pi into 4. Okay.
Hmm.
Now the question is, we have got in terms of theta, so that can vary. This stacking factor can vary once you vary your width of the stack, right, or the stepped core. If you make it a smaller, this value of KST will change. Or if you make the width lesser, your stacking factor will change. But the question is, at which value maximum will occur, right?
Zero.
So for for zero, how come?
Cos 0, 1.
For 0 cos 0 is equal to 1 cos square theta. So to be certain, we can differentiate with in terms of theta, right?
Hmm.
So if you differentiate in terms of theta, this term here, it will come out to be 4 by pi 2 cos theta is nothing but minus sine theta minus cos square theta is
2
2
into
cos theta into
sin theta.
sine theta into plus. This will change into plus, right? Because the differentiation of cos into minus sign, right?
Yes, sir.
This minus should have come here, but I have adjusted here. Now we have to equate it to 0. So 4 by pi 2 cos theta sin theta is equal to sin 2 theta minus 2 sin theta is equal to 0. Now, this value will be
Sin okay.
oh no, one mistake I did here. See, 2 into cos square theta differentiation will be sin square theta, isn't it? If you assume t is equal to cos theta, so dt by d theta is how much? 2 into minus sin theta into cos theta. I think it is same. No, I think it is correct. It is correct. Yeah. So if you equate it to 0, the value you will obtain from the solving this equation, that will be the maximum value of theta. That will give you maximum stacking factor. Okay. You can solve it with help of scientific calculator as well.
Yes.
And from lecture, if you will see, this value has come out to be some 31 degree. So you see how 31 degree is coming. But if you solve, you will get. So this is the basic philosophy behind it. That if you increase the number of stepping, you can optimize the usage of the code. Okay. So in designs or in literature or in the lecture also, there is one slide where professor mentioned that for 2 stepped, this stacking factor is 0.79. For 3 stepped, it is 0.84, and so on. It gets increased. Now coming back to the problem here. Okay. Any doubt in this part? Okay.
No,
If
sir.
not, then we can move ahead with the further problems. So see, fifth problem is quite a straightforward. Here you need to calculate window space factor, and you need to put the value of kV here. So which value of kV will you use to calculate this window space factor? That should be the rating, and rating should be the highest
100
voltage.
kV.
So here just you plug in 2000 volt or 2 kV, right?
Mm.
So only you have to plug it here 10 divided by 30 plus 2. That will be your answer for this question, fifth question. Now the important problems start from question 6. That for a cruciform core, which area of iron is related with the diameter of the circle. Okay. 3-phase core transformer given. Calculate the width of largest stamping, whereas net core iron area is given 0.1 mm square and width of the stamping is 0.9 times of circumscribing circle diameter. So can we calculate the width of the largest stamping? Let us solve it. Okay. So now net iron area is given. How much? 0.1 mm square. Cruciform core is also given, isn't it? Cruciform area is
0.56.
0.56 d square. Area of cruciform core is nothing but 0.56 mm square d square. Right, 0.56 d square. The thing is, we have to calculate d, or rather d is given, right? Diameter of circle is given there. So width of a stamping is 0.9 times of circumscribing circle diameter. Right. So since area of cruciform core is given, right, we can calculate diameter from there. And similarly, width of a stamping is 0.9 times. .9 times of diameter, right? Diameter is into. So this is the width, this is the area of cruciform core, this is the area of iron. Okay. Now area of so here can we calculate the diameter of the circle? 0.1 divided by 0. We just saw the process of calculation of net core area and gross core area. Okay. Then in net core area, we are already given 0.1 mm square. So if see what is missing from this problem, a stacking factor is missing. So if nothing is mentioned about a stacking factor, then you can directly equate the area of cruciform core is equal to area of core. So net and gross will be same now. So 0.56 d square is equal to 0.1 mm square. So d will be nothing but under root 0.1 divided by 0.56. How much will it be? 0.42. So this is the diameter of your circumscribing circle. Okay.
Okay, sir.
Now, what do we suppose to calculate? Width of the largest stamping, isn't it? Width of the largest stamping is given 0.9 times of the circumscribing circle diameter. So width is equal to 0.9 into 0.42, which will be equal to 0.42 into 0.9, nothing but 0.378 meters. Meter or millimeter? Mm.
Meters.
Mm. Yeah.
0.37.
So this is the width of the stamping. Okay.
Okay, sir.
Now let us move ahead with the next part, next problem rather. So I think it is clear for you. Now let us move towards the 7th problem. Seventh problem should be easy. I think you can calculate, but still let us go through once. that a 300 kVA 50 hertz and primary secondary ratio of voltage is given. Three phase delta star core type transformer. A specification of the transformer is given, voltage per turn, right? And HB winding outer diameter and inner diameters are given. On the other hand, LV area of conductor is also given. Similarly, LV winding outer diameter, inner diameter, and area of conductor is given. Resistivity is also given. You just have to calculate the resistance. For resistance, you need resistivity, length, and area. Okay. Area you are given, right? Resistivity you are given. Length just you need to calculate. Okay. So how will you calculate the length there?
Rho L by
No, length you have to calculate. So since see, this is asked regarding length or resistance of the wire, and winding is circular, so length will be nothing but the circumference of that.
circumference. 2 pi r.
Circumference of 2 pi r. Or other hand, diameter is given, right? Diameters are given, so pi d.
Pi
Now,
d.
the thing is that which diameter will you have to consider? Outer diameter or inner diameter, or average of them?
Outer diameter.
No, since you are calculating resistance here, so to average them, because see, in a
What
core,
exactly outer diameter in LV winding outer inner, no?
yeah. So see, outer means there will be one turn that will be the closest to the core. Now you keep winding, keep winding, keep winding.
Yeah, going far actually from the.
Yeah. So this is the outer.
Mm.
This is the inner.
Mm.
To have close to accurate, you just take average of them, right? So average diameter will be nothing but just the addition of them. For example, for HB, 0.36 plus 0.29 divided by 2. If you do,
Yes.
you will get the average diameter. Just
Yeah.
plug in here L is equal to pi d average. You will get the value of resistivity or resistance.
0.325.
Yeah. So 0.325 you are saying average
Yes.
diameter of
Average.
HV. Yeah.
Yeah, HV.
Yeah. Yeah. So I hope you guys will be able to solve this, right?
Will sir.
Okay. Yeah.
No, always. Area
Resistivity
we
is
know.
given, area is given.
And area given, and average we can do for HV winding, average we can do for LV winding, and
Just plug in the length is equal to pi into d average.
yes sir.
Okay.
Yes sir. We will do that. No problem.
Yeah. Now let's consider the eighth problem. Okay. Here we need to calculate height of the window and width of the window. 180 kVA 50 hertz single phase core transformer. A cruciform core is used with distance between adjacent limbs equal to 1.8 times the width of core laminations. Assume voltage per turn as 8 volt. Maximum flux density is given. Window space factor is given. Right.
So that is
What is
not appearing. Seventh question is appearing here.
it?
Yes sir. Still seventh question is there. Yeah.
Oh,
Yeah. Now it
now
is eighth question came 180 kVA.
okay, okay. Yeah, so please see it once. So distance between adjacent limbs are provided, right? That is equal to 1.8 times of width of the core laminations. Voltage per turn is given. Window space factor is given. The space factor is what? Area of copper divided by area of window.
Window.
Current density is given. Net iron area is given. width of largest stamping is also given. Now, how can you use all this data to solve the problem?
Sir,
Yeah.
in the previous question, 7 question,
Uh-huh.
there is an inner winding diameter and outer winding diameter is given.
Mhm.
So why to take average? Why not take the difference?
Okay, so if you'll take difference, see, diameter of wire is being asked here. So the area is how much? If you are calculating area of any circle, because this is in circular form, if you will take difference only, right, it will not make much sense because it will be much lesser than that and it will reduce your value of resistance. And how do you calculate area of any circle?
No, like pi r1 square minus pi
See,
r2 square.
yeah, okay. For simplicity, let us suppose you have a circle like this. Okay. And so how do you calculate area of this circle? Nothing but, let us suppose R1. Area is nothing but pi R1 square. Now, again, you have another circle which with radius of R2, you calculate pi R2 square. If you want to, get cross section area, just a second. If you want to just get the cross sectional area, then you can do pi R2 square minus pi R1 square. Okay, you are getting my point. But that is not the scenario here. The scenario here is you have windings in all over the place. So you just cannot ignore, you just cannot take the difference here. Are you getting my point, Dinesh? So this space is not vacant. Here, all over windings, wires are there. So you cannot know the exact location of all the wires. That's why you have to average it out. Did it answer your question, Dinesh? Do you have any other doubt? Or still not clear?
This we are doing for the calculation of the length of the wire.
Yes, yes. And for length, we need diameter.
So if I calculate like 2 pi r2
Mm-hmm.
minus 2 pi r1 into
Huh.
n,
Okay.
whether it will give the length
2 pi r2 into.
minus 2 pi r1 into n.
So you are saying 2 pi r2 minus r1 into n. You are saying this, right? 2 pi r2 minus r1 into. Mhm. I think, see, you are doing, subtraction here, but subtraction will not give you, accurate, because for this problem, if you want to solve it, what will you get? The difference you can also see by calculating them how much difference you are getting between these two methods. But since you are, I got your point that you are saying that you are considering a wire here at outer and an inner, and you are multiplying, and you are taking in account all the number of terms. But With subtraction, I would say that will not give you exact value, but still I have to think over it. Hmm, that's a good question. I'll have to think over it. R2 minus R1 into N. Yeah, that seems to be reasonable approach. You solve by both the methods, and please let me know how much difference you are getting. I'll also try to solve on my side. Or have you solved already this part, Dinesh?
I will do that.
Oh, okay. So that we can discuss, and it should be close, if not much different. But still, please let me know in that next lecture. Okay. But simply 2 pi R2 minus R1 will not give. If you are multiplying with N, then it is making sense. I will not say it is not making sense. It is making sense, but will have to see the difference between them. Okay.
Yes, sir.
Yeah. Yeah. So we were discussing about problem number 8, right? That we need to calculate height of the window and width of window. So we are given with window space factor, current density, right? And all the parameters are given. Can we calculate these two parameters, height and width? So see, we have derived at the beginning of the session that Q is equal to, or KVA is equal to, how much?
ET
2.22, no,
2.22
2.22 into
F
F
into
into
pi
phi
m
m into
into kW
KW, AW
into J.
into J. Okay. I think that's all the terms, right?
Yes, sir. Oh.
Phi m we can further split into BM into area, right? Area of iron. Because here area of iron would be much more handy. Let me think and see if I can insert from. Okay, no. Now 2.22 into F into BM into area of iron into KW into AW into window area. So this window area is very helpful for us because we need to calculate height and width, right? So KVA is given to us, 180 kVA is equal to 2.22 into frequency is also given, right? Frequency is 50 hertz and phi m is given or not. So let us see.
Given 1.2 Weber per meter square.
1.2 Weber per meter square, and net iron area is also given 0.5 d square. So phi m is given directly. So phi m is BM is given Weber per meter square, 1.2 into AI. AI is given, KW is given, AI and KW. So window space factor is 0.35 and area of iron is 0.5 d square. 0.35 and 0.35 and 0.5 d square into area of window into current density is also given, right? Current density 2.8.
8. 2.8.
It is nothing but ampere per mm square.
M square.
So that we have to take care while calculating in units. So here we can have yeah. So d square into AW is equal to 180 divided by 2.22 into 50 into 1.2 into 0.35 into 2.8 ampere per mm square. This is not the unit of entire thing, so this is just the unit of J. So we can calculate this parameter, right? Now,
2.75.
the total value is how much?
2.757.
2.757 mm. No, I think it should be.
We'll change it to meters.
Okay, we will further change it. Now the second portion is area of iron. So can we calculate area of iron because another parameter is given, which is voltage per turn. I think it is given. So voltage per turn is nothing but 8 volt. So voltage per turn is equal to 4.44 F phi m. With the help of that, we can calculate area of the iron. So voltage per turn is 8, right? 8 is equal to 4.44 into 50 hertz into dm is 1.2 into area of iron. Right? And area of iron is 0.5 d square is also given. We can replace it with 0.5 d square. So here we can calculate d, right? 8 divided by 4.44 into 50 into 1.2 into 0.5. How much will it be? The value of d?
1 second. 0.245.
0.245.
Yes.
0.245. And I hope it is in meter or millimeter. I think meter square. No, sorry. It should be mm. Is it or meter? I think meter. Because we haven't taken any other unit in the direct equation. Yeah, so it should be meter. Now we are done with the value of d. So can we calculate area of window now?
Yes.
Is there any doubt till this point? Otherwise, we can explain here. So area of window, we can calculate. We can plug in the value of d square here, 0.245 square. So AW will be equal to 2.757 divided by 0.245 square. How much will be this area? Mm. Mm.
45.9.
Yeah, so it is 45.9
3
into 10 to the power minus 3 because one term we haven't considered this mm square. So if you calculate exactly window area, that's why you have to take care of unit very carefully. So it will be 0.0459 meter square. Okay, you calculated correctly. Okay, there is no doubt about that. But please take care of unit while solving. because you will get deduction in your marks. So this is your window area. Now we have calculated window area and the diameter of the circumscribing circle. Okay. Now another relation is mentioned in the problem, that width of the largest stamping is x times of the diameter. Right. So it is mentioned here that width of the largest stamping is 0.8 d. It is directly mentioned. So width we will calculate directly here, right? Width of the window is 0.8 d, which is nothing but 0.8 into 0.245. It is nothing but 0.196 meter.
0.9196. Yes.
Yeah. So we have calculated the width of the window. Now can we calculate height of the window? Yeah. So height we can calculate from the area of the window, because area also we have already calculated. So height of the window is nothing but area of the window divided width of the window. So 0.0459 divided by 0.196. Okay.
So 0.234.
0.234. Yeah. So is it fine? Or do you have any doubt in this problem? Or do you think we have done any mistake there?
No.
Because we haven't used one important information in the problem. Did you see any extra information there?
180 kVA rating of the transformer.
No, that we have already used. That's why we calculated the first term, right? D square into AW.
Yes.
But we did not use this distance between adjacent limbs equal to 1.8 times the width of the core lamination.
Yes.
Okay. So that if you calculate, then see what difference will it create. Okay. So distance between width lamination, right? So distance, if you are calculating between width laminations, let's suppose you have a core like this. So you do have this limb and this limb, right? So from where to where you will consider distance between limbs. So since the mean flux path is considered from center, so it is advised to or recommended to consider it from the center. Okay. So this width was given, which is nothing but 1.8 times of width of the core laminations. So this is nothing but 1.8 times of width of the core lamination. That is nothing but this A, this width lamination A. Okay. So, and this width lamination can we calculate here? Because width of the largest stamping is given, right? Width of the largest stamping is given as 0.8 D, and D we have already calculated. So this A, this entire distance between limbs also we will be able to calculate. Okay, it might be confusing, but see, go step by step. Okay, this 1.8 times A is given here. Now, the distance between core centers. So this is the distance between core center. Let me write it for you. Core centers is 1.8. Now, width of the core. Width of the core is also given, right? Width of the largest stamping. Stamping is mentioned, which is nothing but 0.8 D, right? 0.8 D. Okay, 0.8 D. D we have calculated. How much? 0.245 meter.
0.245.
So width of the largest stamping we can calculate from here. That will come 0.196, right?
0.196.
0.196. This is the width of the largest stamping. Now you have to multiply it with 1.8. That is what it is mentioned, that distance between core centers are equal to 1.8. So it will be equal to 1.8 into 0.196 into 1.8. So it will come out to be 0.3528 meter. So this much is 0.352 meter. 0.3528 meter is the distance between your lips or core centers, right? Now, width of the window. Width of the window we have calculated, right? Width of the window we directly did 0.8 D, right? But here, width of the window will be how much? That will be width, total distance between the limbs minus core width, isn't it? Width of window is equal to total distance. This is 0.3528, okay, minus D. Okay. So why we are doing it D? Because we'll explain. So D is nothing but 0.245. So this value will come out to be 0.10. So see, width we have to reduce or do minus, right? So since we are considering from center to center, that is why we are considering only one width of the core. So we are not considering reduction of both the core width from the entire this center. Since we have calculated, because we know that we have calculated from center to center, that is why you can subtract only width of any one core, right? So that is nothing but 0.245. So that is the width of the core. So now width of window came out to be 0.10. So this is the width of the window. If you have doubt, I can repeat again. Okay. Now this width you can use to calculate height from this area expression. So see what we did from the beginning. Let me repeat it once. Here. So see, we just needed to calculate height of the window and width of the window. Okay. For that, we took help of two equations. One is with kVA, other is with voltage. Okay. With voltage, we got the area of iron, which we further plugged in the equations of kVA. Right. From the kVA equation, we got d square AW value. Okay. Now, another equation. You are following till now?
Yes, sir.
Okay. Now we had another equation that area of iron is 0.5 d square. So from here, we calculated d and we again plugged in this equation of kVA and we finally got the value of area of window. I hope you are here with me. Now, we had another relationship given that width of the we have another relationship that the distance between adjacent limbs is equal to 1.8 times width of the core laminations. Okay, so that we have to use. So we were given that distance between limbs is equal to 1.8 times width of the lamination. So with this help of equations, we can calculate the width of the largest stamping, which is again given as 80% of the diameter of the circumscribing circle. So you have to use all these 4 or 5 informations to get accurate results. Okay, I hope you will get it once you will try on your own, after the end of the session, then you will get it. If there is still any doubt, we can again discuss in the next week. Okay.
Okay, sir.
Okay, so I hope that is all about today's session. Is there any final doubt I can take? Then we will wind the session. Okay, Dinesh, do you have any other questions, or did you get this part? And we will discuss about that difference between the radius, right? I have that in mind.
Yeah, we next section we will discuss, sir.
Sure, we will discuss that.
Okay.
Okay, thank you very much for joining and happy Saraswati Puja. Bye. Good night. Thank you.
Thank you, sir. Thank you.